Today is Tuesday, day 24. We're going to talk about first law of thermodynamics today. So let's go ahead and look and see what we have. So when we're talking about energy conservation, we show a roller coaster. And on this roller coaster, we have kinetic energy, potential energy, and internal energy. These bar graphs show you how they are. When they go down to the bottom of the hill, everything is equal. When it goes up to the top, of course, potential energy increases because it's getting ready to go down. Kinetic energy slows down, and so does internal energy. As it's down at the bottom of the hill, the kinetic energy, potential energy, and a little bit of the internal energy is getting ready because it's getting ready to go back up. And as you go across, you can see how kinetic energy, potential energy, and internal energy all fluctuates depending on where the car is on the roller coaster. Now, when the internal energy increases, as the kinetic plus the potential energy decreases. So it is known as an inverse relationship. So the first law of thermodynamics says that the principle of energy conservation that takes the place in account of a system's internal energy as well as work and heat. An example is they were giving you one on a toy balloon being squeezed rapidly. This is not isothermic. Instead, there's two processes. Now, if you remember, isothermic is over here, and so is adiabatic pressure is also over here. But when we're talking about this happening, this is not that. It is two other processes. So, the definition of what work is. Work is being done on the system. The balloon and the air inside it, which is the system, are compressed so that the air's internal energy and the temperature increases, then your work is negative. Adiabatic system, so that Q is equal to 0 and that there are change in U equals a negative work. Air being transferred in is transferred outside the balloon. Internal energy of the gas goes down, which is a change in U is negative. So the change in U is negative equals change negative Q, or you can say the change in U equals Q. So it gave you two versions of the system, how things were going in and out of it. So the first thing we want to look at is we want to look at the formula of what thermodynamic formula looks like. This is the formula that you're going to be using during this session. So it's the change in the system's internal energy equals energy transferred in and out of a system as heat. So that is a very important word. So Q has to do with heat, W has to do with work, and that also has to do with the energy transferred in and out of a system as work. So on the next page, it has the four processes of first law of thermodynamics. You have the isometric, where no work's being done. You have isothermal, where no change in temperature or internal energy is being done. You have your adiabatic system, which no energy transfers as heat. And then you have what's called an isolated system, where no energy transfers as heat, and there's no work being done by the system. So in the book, it gives you a sample, and in that sample, it gives you these types of questions. So let's look and see what the question is asking for our sample. It says a total of 135 joules. Well, that's the work done. It's done on a gaseous refrigerator and is undergoing compression. So since there's work being done, it's going to be a negative number. If the internal energy of the gas increases to 114 joules, that's the change in U. During the process, that the amount of energy transfers is heat. So we are looking for Q. Okay? So what we're just doing here, it's very simple. We're just taking the change in U plus W. So the only thing we're doing in our calculator is we're first of all going to check and make sure we have normal and then radian, because this is not anything that's difficult. So we're going to do 114 plus, and then when you do a negative, go ahead and put your bracket, your negative 135, close your bracket, and you should get a negative 21. And remember, work has to do with joules. So let's look at the practice problems that you had to do today. So number 1 says heat is added to a system and the system does 26 joules of work. That's our work. The internal energy increases to 7 joules. How much heat is added to the system? So what we're going to do is we're going to take our W and we're going to add it to 26, because here is our formula, but that has an unknown variable that we need to change the equation. And so since we're going to have to change the equation, we have to add instead of subtract here. So you take your 26 and you plus your 7, and that's going to give you your 33 joules. Question number 2 says the internal energy of a gas in a gas's engine cylinder decreases 195 joules. So since it's decreasing, it's a negative number. And 52 joules of work is being done. So what we're going to do here is we're going to add our negative. So since it's a negative, you're going to do your bracket, negative 195, close your bracket, and then you're going to add 52 joules to that, which gives you a negative 143 joules. Number 3 says a 2.0 kilogram quantity of water is held at a constant volume and pressure and cooked heating on a range. Okay, so that's just fluff. It says the system's internal energy increases to 8.0, that's the change in U. However, the pressure is not well insulated and the result is 2.0 times 10 to the third joule. That's how much was lost of the energy and transferred to the surrounding air. So since there's no work being done here. So since there's no work being done, so what we're going to do here is we change our formula where we're going to do our change in Q, which is 8.0 times 10 carried to the third power, and we're going to add that to 0, and then we're going to take 2.00 times 10 carried to the 3 over enter, and we get 1,000. And if we want to change that to scientific, then it's 1 to the power of 4. Okay? Either one of those answers are correct. Number 4, the internal energy of a gas decreases to 344 joules. So since it decreases, that's a negative number. And then adotic, how much energy is transferred with the heat, how much work is being done with the gas. So if we're looking here, since it's adiotic, that means that it's no joules at all as far as what the work's being done. So what you're going to do is you're going to take your 0 and you're going to subtract that by a negative 344, and that of course is going to be 3.4, but if you change it to normal mode and then do answer, you get 344 joules, which is a positive number. Because if you subtract a negative number, will be a positive number. Number 5, a steam engine boiler completely covers 155 kilograms of water of steam. Fluff. The process involved in transferring 3.5 times 10 to the 8. That's our Q. If the steam escapes through the system valve at 1.7 times 10 to the 8, that's our work being done. And the work expands against the outside atmosphere. What is the net change in the internal energy of the water system? So the one thing we're going to do here is we're going to take 3.5 times 10 caret 8, and we're going to subtract that by 1.76 times 10 to the 8th, and we get 174 with a bunch of zeros. If we change our mode to scientific, we get 1.74 times 10 to the 8th. The only thing else left in the reading assignment is this cycling process. So when we're having this cycling process, is a thermodynamic process in which a system returns in the same condition under which it started. So it's kind of like a cycle, okay? So it gave you some examples of that. And it said the change in U net equals O and Q net equals W net. Heat energy uses heat to do work similar to a water wheel. So it actually showed you this heat engine and how the steam engine transfers energy from a higher temperature substance to a lower temperature substance, which is W net equals the high temperature subtracted by the low temperature. And then after that, it gives you a stem about a gasoline engine, and it also gives you a stem about a refrigerator. What I would like you to do also with this today is I would like you to read both of those stem ones. And what I would like you to do is give me just a brief summary of the refrigerator one and the gasoline engine one. And just you can do a diagram, you can do a Venn diagram, you can just write down what you think. But I do want you to look at those two diagrams, and you can even do like a rough explanation of what they were talking about, how a refrigerator works, how gasoline engines work compared to a steam engine. So if you could include that in today, that would be wonderful. I hope you have a good day, and I will see you tomorrow.